Okay, so number 7 is the first one people want to do. Object 1 starts at 25 meters and moves with the velocity of this. Object 2 starts at this and moves directly towards object 1. Two objects collide after this start. Was the velocity, was the position of the objects when they collide, right? All right. So, alright, so this is number 7. Why are you doing this to me? This is number 7. In my Y, I'm thinking, okay, to collide must be in. Wow, that handwriting is horrible. Maybe I could, let me grab a text box and type. Getting used to this new board is going to be interesting. So we'll grab a text box. And bring that down to 24. There we go, that'll work. So, to collide, the two objects must be at the same place at the same time. One is moving in a negative direction, and the other in a positive direction. But both at a constant rate. Do they have the same amount of time to move? Let's see. Yes. So that would be, I think that would be worth noting. They have the same amount of time to move. How's that? That's good? Does it make sense? Okay. Maybe I can get rid of that. And I think the typing is going to work better than the Mr. Docker handwriting. Alright, so now onto my how. And I need to start with valid physics equations. So I'm going to grab my equation sheet. And looking at the problem, I think I'm going to start off actually with the diagram. Because, and this could have been in my Y or in my how. I'm going to put it in my how just because of my room factor. But we have 25 meters. The object starts at 13 meters and moves directly towards. Okay, so this, and that's object 2. That's object 1. That's 25 meters. It's 13 meters. Maybe my finger will work better than my pen. This is going to be the velocity of 1. This would be the velocity of 2. And let's call right here, they meet. It'll be a while to get used to this new board. So, here to here, I'm going to call that the displacement of 2. And from here to here, displacement of 1. And that direction I'm calling positive. That looks like a T. I'm calling that direction positive. Everyone okay with that so far? Okay. So now I need an equation. And so the equation that I need, this one here, and I'm going to paste that in. Oops. So used to using a smartboard when I can just drag everything. Alright, so let me keep that visible. Alright, so I think I'm going to do a little bit more labeling here. I'm going to call this D1 initial, this point D2 initial, and I'm going to call this point here just DF, location final. Yeah?
I just had a unrelated question. Are you going to have the equations available for...
Always, yeah. No memorization, understanding. So, I'm going to rewrite this slightly. I remember that delta is always change, right? So it's final minus initial, like it's written on the walls. So I'm going to put D final minus D initial over the amount of time that elapses, delta T. And that's true for each of them. So if I rearrange that, I can say, well, their velocity times delta T equals D final, which is a vector also. Oops, I forgot my vector symbol. Minus D initial. Is everyone, yes, following math? Don't worry, I'm recording all of this for you. And it'll be up. But you're welcome to take pictures also. So, I'm going to do one other rearrangement here. Because I know that they end up at the same final position, right? So I can bring this DI over to the other side and make it positive. I can get that over by adding it to each side. So I'm going to have DI plus V delta T equals D final. Oh, wait a minute. That's one of my equations. I could have just started there. Whoops. Those two are the same thing. This is one of the points. I didn't mean that. I had a Friday brain. But I could have started right there. Oops. Hey, look, proof. Alright, so let's do it for object 1. Make object 1 red. So for object number 1, it's D initial. It started at, I believe it was 25 meters. Object 1 at 25 meters. So DI for object 1 is 25 meters. Plus its velocity is negative 5.4 meters per second. Negative 5.4 meters per second. The amount of time that it moves for is 0.67 seconds. Remember, these are different for you guys, right? And that equals the final spot that it gets to. Yes? Good? Okay. Now let's go on to object 2. Object 2 starts at 13 meters for me and moves directly towards object 1. But it doesn't tell me how fast, does it? So, plus V, I'll call that V2, times 0.67 seconds equals V final. So I've kind of translated what they told me into math sentences now. And they want me to find what V2 is, and also I think they want me to find what V final is, right? So they want me to find V2, and they want me to find the position here. So I can solve the red one to find the position, and then use that in the blue one to find V2. Yay! I solved it. All right? I'll let you do the final math because that's hard. Are there any questions or anything I can clarify? All right, so number 12, finishing on the frame of reference. So background, right? Okay. So then we have our diagram here, A, B, C, and D. Consider 4 cars, an Audi, a Buick, Corvette, and a Domino. Daimler. Noted by cars moving straight stretch of road, their velocity is 3 more time as shown in the diagram. First several questions refer to this diagram. Okay, so I'm not going to do the multiple choice ones, but we'll gladly go through most of them. Well, we'll talk about it. Let's see what we can determine. Let's see what they want to know. So they want to know about switching frames of reference, right? See, they put the slash in between the subscripts, where I don't use that slash, but, and then car ease. So, okay. So here, minimize that. Text. Anybody have a favorite color of text? Orange. Orange is first. Alright. So I need to show that I understand relative motion. So all motion, velocity, and displacement is relative to your frame of reference. That's how I do frame of reference. Capital F, lowercase, capital F. When you change frames of reference, the velocities will also change. And in the same frame of reference, you are not moving. Yeah, I think that's pretty good. What do you guys think? That shows I understand frame of reference and I understand how these relative velocities are going to change. So, I think it does. And, I'm going to have to play with my character spots to get it to line up. Ooh, I wonder. I was hoping to make the background. No, I guess I can't. So much better. Alright, I think I'm going to copy my diagram into here from my problem, because if I have to just keep remembering it, that will be difficult. So, grab that. And then the equations that I need are my two relative motion equations here. Alright. So that should be all the kind of technical information I need. So if I'm thinking about this, and I'm looking at, right now, I'm in B's frame of reference, right? Because B's not moving in my diagram. That may also be the Earth's frame of reference, right? Reference. So they want to know, for the first problem, the car's velocity shown in the diagram is reasonably assumed that the velocity in the diagram given relative to which of the following? And my guess is, what do we normally refer, what frame of references are we most comfortable with? The Earth. Earth, right. Right. So what is the velocity of A with respect to B? B with respect to A? Can you determine the distance between them? A to C, D to C, C to D, car E is moving on station through, not shown there. Okay. So why don't we look at this one? Because, you know, if we were, right now I think we're in the reference frame of B. So if we were looking at, if we were looking at the velocity of C, if I was to express that right now, so if I would say the velocity of C, that would be with respect to B. You guys okay with calling this direction negative? So that direction positive? Is that okay with everybody? Okay. So, velocity of C with respect to B is, for me, is negative 15 meters per second. It's negative because it's pointing to the left. And then if I use my second equation here, the velocity of B with respect to C would be the opposite of that, or negative and negative, which is positive 15 meters per second, if I'm just swapping between the two frames of reference. If I'm doing more than that, so let's look at the last one here. The Edsel moving on St. Stitch Road and not shown in the diagram is known from the point of view of the driver of the Audi. The Edsel is moving at 8 meters per second. So velocity of the Edsel with respect to the Audi. Why are you messing with me this way? Wow. something. Not liking something I'm doing. Velocity of the Etzel from the Audi is 8 meters per second. Right? What is the speed of the Etzel relative to the Daimler? So we want to know velocity of E with respect to D. So I'm going to use this equation up here. I'm going to say, well, the velocity of the Etzel, E to D, I'm doing something. Anybody have any idea what I'm screwing up? That would be the velocity of E to something plus the velocity of that same thing to D. Remember, the two B's have to be the same. So I know E to A, so I need to find A to D. Right? Well, let's see. I know A to B, but I don't know A to D. Oh, but I know A to B, and I know I can find out B to D. Right? Yeah, I can. I want to work below this, sorry. Let me move my diagram so it doesn't disappear on me. There we go. So, I don't know A to D. But I could find out, I could say, well, V A to D equals V A to B plus V B to D. And then V B to B equals negative V BD. I know, lots of letters. Most subscripts will use all year. D to B, I know. That's negative 20 meters per second. That's from that diagram. And that equals my negative of VBD. That means VBD, 20 meters per second. VAB for my diagram is positive 12 meters per second, which means I can find VAD. What would VAD be? .32 meters per second, 12 plus 20. And then, hey, I got VAD. I know EA, so I can get my answer. Yay! Relative motion ones are a lot about, can I keep track of what I'm doing and what order things are in. All right. We're going to do number 11. We have a baseball with certain momentum, and just before it hits the ground, and they want to know what's the ball's speed before landing. Let's go here. I'm wondering if 20, I just want to see if 20 will fit. So, momentum is based on the object's inertia and its velocity. 20 didn't work well. The inertia is measured by the mass, and the speed is related to the velocity. Having on it, try 18. That's better. So maybe 18 is the font size I need to use. Seems to work. That's too small to see or not? Is that good? That's good? Okay. Oh, I spelled measured nicely. Just threw a W in there just to see it. Wow. Alright. On to the how. The how. We need this. We need our snipping tool. New. Grab our momentum. Back here. Paste our momentum. And now it's really plugging in now. Alright, so we're told that the, where is it, right here, that it's 0.15 kilograms and 0.7 kilogram meters per second, and they want the answer in meters per second, so we don't even have any units to change. So really, it's plugging it in, so 0.70 kilogram meters per second, 0.15 kilograms times V, solve for V. And what's nice is we'll find the velocity, but the speed in this case will just be the magnitude of the velocity. Alright, so you just do the opposite then. Notice I'm substituting it with units. I'm doing all the steps to hit that rubric. Right? Alright, that's good. I'm gonna